So I apologize for this. That's never had that happen to me before. Right. Yeah, Google's got vicious over the weekend. Right. Newton's law. So the first law. Which I hope you all remember from GCSE, an object will remain at the same speed unless there is a resultant or unbalanced force acting on it. Right. So this object here will remain at a constant speed, which could be 0. This object here will remain at a constant speed, which could be 0. This object here, same thing. Okay. What's the tendency? There's one word that goes with this, the tendency of objects to keep doing what they're doing. Yeah, sorry about that, Kira. I don't know what happened. Hi, Razan. Razan, I've recorded the first couple of minutes of this lesson, so you haven't missed much at all.
Thanks, sir.
Inertia, good. Right, so objects have inertia, which means they want to keep on moving at the same speed. So if you try and push something, if you try and push a chair or a book or something, it doesn't want to move because it has inertia. If something's already moving and you try and stop it, it doesn't want to stop because it has inertia. And inertia is caused by mass, right? And it comes from the Greek word that means laziness or just lazy, which it kind of makes sense in its meaning. Right, that's fairly straightforward. Newton's second law. Oh, sorry, which bit? This bit here. Yeah, it says the tendency, which I think I've spelled completely wrong, of objects to keep doing what they are doing. The tendency of objects to keep doing what they are already doing. Newton's second law, really simple. It's basically summed up in this equation: forces, mass times acceleration. Now we're gonna, in a couple of lessons' time, look at a better definition of this, which is forces mass times velocity minus mass times initial velocity over time, or mass is change in momentum over time, and that obviously comes because because acceleration is change in velocity over time. But we're not going to worry about this for now. All right, so here we go. This is 2 kilograms. What's the acceleration going to be? Obviously, 5 minus 1 times by 2. No, it's not. 5 minus 1 over 2, which is 2 meters per second squared. All right, really easy, really straightforward. But of course, they're not going to make it that easy for you in an exam. They are, of course, going to make it significantly harder. So there's a couple of situations we're going to look at for the second law. So in order to make this as correct as possible, we should probably write it like this: the resultant force or the net force. Okay. You can write resultant, net, or overall, it doesn't matter. right? Which is what we instinctively know, but we sometimes forget. And the reason it's worth pointing out is because if we start looking at more complicated situations, right? So here's a rocket. What forces are on it? We've got its thrust, and what force is obviously also acting on it? Weight. So therefore, how do we work out its acceleration? Well, its net force is its mass times its acceleration. So the thrust minus the weight is mass times acceleration. So acceleration is thrust minus weight over mass. Right, it's amazing how many people forget when something is moving up that there is obviously a weight acting down. The other common example, and I don't know why physicists and mathematicians are so obsessed with lifts, but they really are obsessed with lifts. We've got, again, some force up, which we might call tension. And then obviously there is a weight acting down. And there's two cases for lifts, right? It could be accelerating up, in which case tension minus weight is equal to mass times acceleration, right? Because this is bigger. Or it could be accelerating down, in which case this force is bigger. So weight minus tension is mass times acceleration. We might have other situations. We might have situations where there are pulleys. Let's call this little m, and let's call this big M. And the homework this week actually has one of these types of questions in, which is quite a tricky question. So what forces are on here? We've got a tension in the rope. It must be the same because it's a single rope. And then we've got our weight. Right, little m and big M is like two really stupid letters to use. Like M1 and M2 might be better. But this encourages you to have really neat handwriting, otherwise it doesn't make any sense. So supposing it is accelerating this way. Then we've got a couple of different things to consider. Right, let's look just at this one first, the big one. What's happening for the big one? Well, we always need to start with this. F net is mass times acceleration. So for the big one, it's accelerating down. So which one of these forces is bigger? Obviously, it's weight. So we can write mg minus tension is its mass times its acceleration. What about for the little one? It's accelerating up. Which one of these forces is bigger? Tension must obviously be bigger for it to accelerate up. So tension minus weight equals its mass times its acceleration. Right. Now we can solve these. So our old favorite simultaneous equations. Right. Because we've got two things that we don't know, the tension and the acceleration. Right. Obviously, the acceleration is the same because they're connected by a string. So if this accelerates down by 5 meters per second squared, this one will accelerate up at 5 meters per second squared. And the tension is obviously the same because it's a single piece of string. If it wasn't constant, then it wouldn't accelerate in the way that we expect it to. Right, two more quick situations. Often we also get things like cars pulling trailers. And we have to be really careful here when we analyze this. We have to think about sometimes them individually and sometimes them together. Okay, so there'll be some force like the engine thrust. There might be some force of friction, for example. So again, F net is the resultant force. I'll put FR just for friction, equals mass times acceleration. In this case, what's the mass? The mass is m1 plus m2. So the overall equation FR minus FR is m1 plus m2. Right, so that tells us the acceleration of everything. Now, sometimes they'll say something like, what is this force here? What should we call this? Let's call this F2, the force on 2. Right, and you might, think it's the same as the thrust, but it's not always the same as the thrust, because if this mass is tiny, it doesn't need the same large thrust to accelerate. So if you were just looking at M2, then you would say that F2 is M2 times the acceleration. The acceleration is the same as this one. The mass 2 you know, and you can find out the force. Right? And there can be some really quite tricky problems using this idea where you might have 3 or 4 things connected together and they try and confuse you, right, by just asking for one of these individual forces. And then the final situation we're going to look at are things on a slope. So what are the forces on this on the slope? Mass times gravity, which is weight. Reaction force. There may or may not be friction. Sometimes we have it, sometimes we don't. So how do we solve this for a slope? Well, we need to get the weight, and we need to split the weight up into its components. So we know that this component of weight is mg cos theta, exactly the same as we've done loads of times before. This component here is mg sine theta, just like we've done many times before. And now, what is the equation of motion? So the resultant force is mass times acceleration. If it's accelerating down the slope, mg sine theta minus friction, if it's there, is its mass times its acceleration. And this is useful because then we might be able to find friction if we know A, for example, or we can find A if we know friction, right? So this is very useful. You'll notice all of these situations we use exactly the same method. It's a simple method, one simple equation we learned in GCSE, but the situations can get increasingly complicated. Right, are there any questions at this stage? All right, final thing before I say on some questions is Newton's third law. So I've got a little question for you. If you could spend a minute reading this and thinking of your answer. Hopefully you can see the PowerPoint. If you can't, you might just minimize my screen. All right, please put your answer in the chat, A, B, C, D, or E. Naveed, which do you think is most likely, even if you're not 100% sure, which is most likely? Okay, so Newton's third law, as we all probably remember GCSE, for every force there is an equal and opposite reaction. There's an equal and opposite force. So B is the most common answer. So let's look at this. So we've got the force from the horse on the carriage is equal to the carriage on the horse, because every force has an equal and opposite reaction. And you think that the carriage will move because the horse pulls slightly harder than the carriage. So does this mean then you think that Newton is wrong about his third law and every force does not have an equal and opposite reaction? Let's pick on Ahmed.
Sorry, so what?
B. Could you maybe just explain your answer a little bit more to B?
I don't know, I just guessed, so to be honest.
Guess. So if every action has an equal and opposite reaction, if the horse pulls a little bit harder, what's going to happen to the reaction force going the other way?
It would increase.
It will always increase, so they cancel out.
Mm.
All right, so that's not the answer. We had one shout for A, which sounds completely logical, right, if the forces are balanced. However, can that be correct? Because do things move? Do horses pull things? Yes. So this can't be the answer. So there must be something else. Akira, you put E. What is your explanation for E?
I just knew it couldn't be A. I just knew it couldn't be A, couldn't be B. I thought it couldn't be D because there's things that can pull things that are heavier than it. And I thought it might be C, but then I wouldn't know how it works, so I just said E.
Okay, so very sensible process of elimination. And you are obviously correct, it is E, but we need to know why. Amirali, you've also put E. What do you think?
Has it got to do with friction? So something experiences more friction than the other, and thus, like, one is able to pull the other.
You are on the right lines.
Um,
So where is there friction?
so there's probably more friction on the carriage. Well, actually,
Where?
where? At the back.
What, here?
Yeah.
Well, what's causing the friction in like halfway up the carriage?
So I do not know where the friction is.
So the friction occurs when two things rub together, right? Like
yeah. So it's like at the tire, at the bottom of the tire.
Exactly. All right. And the friction, there must obviously be friction on the horse's feet. Okay. And then there is obviously this force here that's pulling, the horse is pulling forwards. So what do we need for the carriage to move? We need the forward force from the horse to be greater than the force of friction on the wheels of the carriage. If that's true, the carriage will move, right? Where does the horse get its pull from? Well, it gets its pull from the fact that there's friction between its feet and the ground. So as long as this force here is greater than this force of friction here, it will move. Right, so this question is designed, it's designed to confuse forces and muddle them up and get you to think about the third law pair here, when that's not really the explanation. The explanation is about the friction compared to the friction here. So you can all basically see this for yourself, right? If you try and push the piece of paper in front of you, it will obviously move, right? Because you're very strong, the force of friction between the paper and the table is very small. But if you go to the wall and you go and try and push the wall and you push it really, 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 really hard, what's going to happen? The wall isn't going to budge an inch because it's stronger than you. What's going to happen to your feet? They're going to start sliding on the carpet if you push hard enough, or sliding on the tiles on the floor, or the wood on the floor, depending on what you have, right? And you'll find that the friction is not large enough, so you will start to move. That's what, is what's going on here. Lots of friction here, not much friction here, it will move. So how does this relate to Newton's third law? So it is for every force, so for every force there is an equal and opposite reaction. So for example, if I draw a table and I draw on this table a nice pair, right, what's the Newton's third law pair here on my pair? Right, if I draw the weight here, what is the third law pair? Right, you might say it's the table pushing up, but that's not the third law pair. The third law pair would be the weight of the pair pulling the Earth's gravity. Right, there's also another third law pair here as well. So I'll draw my second pair. There is also the pair that is the table pushing up on the pair and the pair pushing down on the table. And that is also a third law pair. Okay. The object will move if, for example, the weight is greater than the reaction force. Right? If it was a really heavy pair and the table couldn't push back enough, then the table would collapse and it would move, for example. Right? Or let's look at another quick example. Supposing I have my pair and I've chucked it out the window because it's moldy. Right? It will obviously start to accelerate down. Right? Because the weight is greater than the air resistance. But this is not the third law pair. The third law pair is still the weight of the pair and the force of gravity on the Earth from the pair. It's also, the third law pair would be the air resistance and the force of the pair on the air particles. So what we need to have a third law pair is the forces must be the same type. So both gravity, both contact forces, both friction, etc. They must be equal in size, opposite in direction, and then both must act along the same line. So what I mean by that is this is all along the same line, so this is fine. Okay, if I did if I drew an object like this and did two forces here and said this was 3 newtons, this was 3 newtons, they're not along the same line, so that is obviously not a third law pair. If I look at this example here and I look at this weight and this friction, not along the same line, not a third law pair. Okay. All right, that is enough talking for me. If you have questions, please ask them. If not, please start to work through the tasks in the class, in the lesson. There are 2 videos for worked examples, one easier and one harder. If you find the first one is too easy and too straightforward, don't feel you need to do every single example in it. You can skip onto the second one. When you get onto task 4, you again have 2 options. You can pick the easier one, or if you're confident, you can just jump straight onto the exam questions. You have the rest of the lesson for this. I don't think you'll get through everything in the thing, but obviously if you do, I will provide you with more things.